So you've already seen kinematics before. Displacement as s, velocity as v, acceleration as a. Easy to remember because it makes the acronym SVA. And we know that one is the derivative of the other. So you can get from displacement to velocity with the derivative, from velocity to acceleration with the derivative, and you can integrate back. So we've done these questions before, but we were always dealing with derivatives. Now we can pose questions where we start with an equation for acceleration and then work backwards to find out what the equation was for velocity, and work backwards again to find what the equation is for displacement. Now, if we want to find out what the c and d values, because every time we integrate, we have to go plus c. And if we integrate twice, we go plus c and plus d, and we've done those questions before. So you need certain things along the way, or certain starting points, in order to find those values. Now, here we are. We want to find the equation for velocity and displacement, given that at displacement is 0 when time is 0, which is a very common thing, unless you're measuring it based on another fixed point. And when time is 0, our initial velocity is 8 meters per second. So if we say, well, the integral of my acceleration, which is t plus 1, that will be my velocity. Then I get my velocity to be t squared over 2 plus t plus c. Of course, we know that at t equals 0, our velocity was 8. So if we plug those things in, what could c possibly be? And so now we know that our velocity equation is actually t squared over 2 plus t plus 8. And if we want to find our displacement, we're going to have to integrate our velocity formula. I start making my t's loopy so that you can't, you can tell that they're t's and not plus signs. It's very hard to square a plus sign, though. And add 1 to the exponent and divide by that number. We'll get t cubed over 6 plus t squared over 2 plus 8t. Oh, I said I'd make them loopy. There we go. Plus d. And we know that our displacement is 0 when time is 0. So plugging in 0 for t and 0 for displacement, you will get that d is equal to 0. So our equation for our displacement is just t cubed over 6 plus t squared over 2 plus 8t. And did we solve everything? Yes. If you go back in time, but if we would look at, like if we were to graph this, first of all, you could factor out a t, and then, but if we just go to our graphing calculator and look, ooh, we got an x cubed in there already. That's nice. And then it's divided by 2. And then plus 8x. Nice. So we, oh, it is, there it is. So let's zoom here and let's make it fit a little bit better. It's a very boring cubic graph. But there isn't any of those hills and valleys in this one. Partially because if we were to go back to here, right, you know that you could factor out a t. Okay? Just to make things nicer, I'm going to factor out a t over 6. That'll leave me with t squared plus 3t plus 48. Okay? As far as where our x-intercepts go, we know that there's just the one. This, if you use the quadratic formula, will have no solution. So that's why there's only the one x-intercept at 0. Looking at our velocity, which is our derivative of our displacement, if we look at our velocity equation, up a little bit, t squared over 2 plus t plus 8, it's also never equal to 0. If you use a quadratic formula on this, you'll get a negative discriminant, which means that v never equals 0. If it never equals 0, as far as our lines go, all we'd have to do is plug in a value here and see what happens, and we'll notice that this parabola is always above the y-axis, which means it's always positive, which is why our function is always increasing. So we're never changing directions. Okay. So you can use calculus to interpret these things. You can use your graphing stuff to look at what it means for a function as well.